When we go to the areas that are impacted by wildfires, basically post-event investigations, we see a common pattern that regardless of what building materials were used in the building, they all failed in some cases. So in other words, if the building was built in the 70s, 80s, 90s, it doesn't really matter. They all had different building materials and the heat was so high that it overwhelmed all of these building materials. So that was the question that we had in mind, and by we I mean the whole fire community, that what is the proper exposure that we need to test building materials against? And based on that, what should we expect? We didn't have that data 4 years ago.
What we are trying to answer is what is the safest distance between two structures.
The secondary goal here is our member companies maybe don't understand what heat flux means. So we need to package these data in the right way that they can use it in CAT models.
So other researchers have burned structures before, but they don't have that wind element, right? They don't have the ability to control the wind like we do here at IBHS, where they can burn a large structure and just dial into the wind to exactly the conditions you want.
The third audience for the results of this project is builders and homeowners. Builders can basically look at our guidance and choose the right building material based on the structure separation distance in a neighborhood. For homeowners, they can actually look at the added risk that having a secondary building on the parcel adds, and then they can choose not to have any shed or any auxiliary dwelling unit in their backyard. We are pushing the envelope of what we know about wind-driven fires, and that's very exciting.
Faraz came to me and said he had an idea of burning multiple buildings, and similar to what we were already doing with the structure separation experiments, and where we used various size sheds to against a target house, and he wanted to take that to the next level utilizing ADUs, which stands for accessory dwelling units.
And in phase 2, which is the ADUs, we're building on top of that. So we are burning realistic fuel load, common building materials that you see in the field. In California, Colorado, in many parts of the country, you see the same materials that is used in this test campaign. And for the first time, we can quantify this exposure from a burning structure to the target building. And those are the overarching goals.
You know, most of my work was just putting what Faraz wanted on paper that would better the science. And after that, after the design, it was creating truss layouts, creating the floor plans, getting all that squared away and making it so that our team, our carpenters, could build it.
The actual building of the house, we putting the floor in first, the foundation going in first, walls, then setting trusses, then we put the roof on, get it dried in, then we go put siding on, and then from there we start on the interior work.
So about a week before the scheduled experiment, things start to pivot, right? We would go from a team of carpenters that are building houses and installing flooring and getting everything ready, and we shift over to a more technical component, right?
So is that the top? Yeah, the top. It says T on it. So yeah. So then this one's wired correctly here.
My name's Lucas Faulkner. I'm the instrumentation technician here at IBHS.
The top E-flux is fluctuating backwards, so it's going down instead of one we would expect it to go up. So we're looking at the wire. It's probably wired backwards.
The main goal that we try to do is making sure everything goes in smoothly, and then the data that we are collecting from the fire is clean data and smooth data.
Moving just a single wire, it can cause some kind of interference, or you can lose an electrical connection. So we have to go back through and double check everything. That's what the puff test is for. So,
HF4. So for the thermocouples, we can just take like a heat gun and test it, touch it with it, and just making sure that that is going from a known temperature, which is usually the air temperature that we can just check with our on-site weather station, and making sure that is going, rising above that temperature. And then we will also test it with ice to make sure that it is dropping to near zero.
So when we run the puff test, we send that data to the researcher. We go through and find what's wrong and are we getting good data
So my role in ADU tests is to work closely with researchers, the fire researchers and the instrumentation team to make sure that we collect high quality high quality data. So sensors are the gateways for collecting data. So basically any physical phenomenon that you want to study, you need sensors to collect data. Given the unpredictable nature of these tests, and because they create or generate embers and extreme heat, so this poses risks to our instrumentation system.
Two of them vertical placed over there between the two legs, and the reason is I want that to ignite and then use the legs to go up and ignite this. Gotcha. So I want a continuous vertical fluid path.
So when we were looking at furniture is one of those things that year in and year out changes. And we wanted to make sure that we would be able to get the exact same thing so that we're using exactly the same thing in each experiment.
So we are trying to recreate a more realistic heat source. And with a more realistic heat source, we will want to know what will be the extent of the exposure and how different building materials will perform to that exposure.
So we're putting shoes and books and clothes, woody goods, so wood bowls, wood decorative things. We've had little cat houses and trash cans, potato chips. There is vegetable oil in the cabinet that represents. We want to represent as much as possible a real structure that's lived in.
So you're really in a rush to get everything operational and working, because you can't do it a week ahead of time because it's going to sit out in the elements. So it's really a lot of busy worker bees working all over the place to get the thing set up.
I think there's around 250 sheets of 4x8 drywall at half-inch thick. So every experiment, 250 sheets per experiment. So it's quite a lot of drywall. We could do the math on how expensive that is.
So we learned that the concrete, we were reaching temperatures during these burns that were extraordinarily high, right, on the concrete. And we realized that we needed to protect our concrete. First of all, we didn't want to damage it too much, right? But bigger than that is in one instance when we had some trapped moisture inside the concrete, and we had not put enough of a protective barrier between the burning structure and the concrete, we started seeing this spalling. And what happened is the moisture that was trapped inside of the concrete turned to steam and started to expand rapidly. And the surface of the concrete started popping, and big chunks of the surface of the concrete started flying into the air, endangering everyone there was there participating in this experiment. So the amount of drywall that we've used just to protect the concrete on this project has been impressive. We have used a tremendous amount of drywall.
So my job starts a little bit earlier, not the day of, to look at what should be the structure separation distance. Where do we want to put the sensors and the cameras, or what wind trace we want to run, what wind speed, 35 miles an hour, 65 miles an hour. Those are the questions that I try to answer a few days before, and then I communicate that with the team. And then the day of, to me, is just watching 30 purposeful people walk around, and they all try to make it happen.
And it is typical on the day of the experiment to have as many as 30 people involved in this experiment, all in different capacities. And it is exciting to see. It is very cool to see everybody pulling together and making it all happen.
First of all, thank you everyone for being here today. This represents the number 6 ADU experiment. What we're doing today is we have a 625 square foot ADU on a 45-degree angle to our wind, with 10 cribs loaded in front of it and a target house beyond it. We'll be looking at wind speeds of about 35 miles per hour.
There's a lot of different pieces and things that can go wrong, and that's especially true in wildfire. In the case of a lot of our testing, if we have something go bad, we just push the stop button, we reset, and then we go again.
Peak heat release. So we expect from ignition, the flashover to be about 3 to 5 minutes after ignition. The peak heat release will be between 15 and 20 minutes.
In the case of wildfire, Well, that process can still happen. It just means rebuilding an entire structure at that point because the fire's actually destroyed it. So there's a lot of challenges.
Risks, obviously, we have fire risks, which include burns, flying ember, debris. Mitigation for that, we will have 2 teams with fire hoses, and Richburg Fire is here with us as well. All operations team in position, product in position, handing it over to research. On your mark.
Lucas, with fans are at idle speed, we can confirm the test selection as 23 cal, 35 to 40 miles an hour. Are you ready?
Yes, Instrumentation is ready.
Yep. All right, test is confirmed. As they say, you have the con.
Start data collection in 3, 2, 1, start.
20 seconds to ignition. Ten. 3, 2, 1. Ignition.
For the external ignition, we run some tests with wood creeps in the simulation that allowed us to see how many wood creeps do we need to create a consistent heat exposure that will generate the larger peak heat release rate, which is what we are looking for. We are looking to what is the configuration that creates the worst case scenario for the future test.
Eaves on fire.
Yeah. Go to Eve, please.
Eaves are on fire.
Eve 137.
It's something that everyone enjoys seeing, kind of these very, very visual experiments that we do. In terms of the operations, oftentimes it's called controlled chaos.
Window just fell out.
Oh, beautiful, beautiful. Okay, is it rising?
It's rising.
These 2 is the upper ones?
Yes, this is upper 2. It's 5 and 6 in the kitchen. So these 2 right here.
Yep.
Looks like it's coming through the door.
Is the window filled or?
The this
yeah,
window,
there you go,
this
there you go.
window
Yeah. Go up, go up, go up.
With these experiments, we are trying to answer, like, even in very windy events, what is the likelihood of survivability?
Go ahead, power up the fans.
Power up the fans, power up the fans.
Fans are coming up.
Flash over achieved. Hey Lucas, what heat flux level are you reading?
The heat flushes in the center window are reading 1112. The center rig is reading 15,000 at a peak of 23. Right there, a peak of 35,000.
So we are prescribed how the sofa burn, how the bed burn, and those are coming from experiments mostly that are run in no wind condition. There is no data of how these pieces burn under wind condition.
It might be the way that the wind's being deflected
Yeah.
around it and then up and off to the side.
Yeah. This is like where the numerical models fail. We modeled it numerically, and this was the worst case, but that fails, you know. It can't predict it. That's why you need experiments.
If you're downwind, be aware that large debris is now coming off of the target or the ADU source house.
So this is a 40% higher surface.
But it's far away.
But it's far away.
Exactly.
So the balance between them, the other one overpowers.
Exactly,
Yeah. I mean, that's good finding.
The front walls look like they're starting to lean in and may fall at any time. Be aware.
I remember I was a first-year PhD student, and I was sitting in a meeting with fire experts, and we were talking about the different heat flux levels based on different separation distances, and what should be the heat flux level and how we should choose the materials to withstand that heat flux level. We all looked at each other and we smiled. We didn't know. And based on that, we had some best opinion or expert opinion based on what we see in the field. And 30 foot, 50 foot, all of those numbers that is commonly known by fire scientists and the public come based on those expert opinion and what people see in the field. And Those are extreme cases, and we know that it's not possible to have all homes 50 feet apart. And 10 years later at IBHS, we tested 23 sheds and 11 ADUs. Now we don't need to rely solely on those opinions. We have data that we can quantify risk, hazard, and basically how likely is it for the fire to jump from one building to the other. Looking ahead, we tested 11 ADUs, all of those were compliant with Chapter 7A. And we see that Chapter 7A, while it might not help to reduce one single home, like the vulnerability of one single home, it does help to slow down the fire spread in the community. And we see that, we have the data to support it. But most of the building stock in California is not built to Chapter 7A. All of those predates that building code. And for the next phase of this project, we are actually looking at that. We're looking at what if the home is not compliant with Chapter 7A? What is the likelihood that the fire jumps from one building to the other under those conditions? And with that, we can close this loop by looking at what do building codes offer and what we should expect basically in California right now.